So I have the graph of y is equal to f of t here. Our horizontal axis is in terms of time, in terms of seconds. And this type of function is often described as a square wave. And we see that it is a periodic function, that it completes one cycle every 2 pi seconds. And so we could say its period is equal to 2 pi. If we want to put the units, we could say 2 pi seconds per cycle. We could write it like that. We could also just write s for seconds. And its frequency is going to be 1 over that. So we could write its frequency is equal to 1 over 2 pi cycles per second. Cycles per second, it can also be described as hertz. And what we're going to explore in this video is, can we take a periodic function like this and represent it as an infinite sum of sines and cosines of different periods or different frequencies? So to write that out a little bit more clearly, can we take our f of t? So can we take our f of t and write it as the sum of sines and cosines? So can we write it? So it's going to be some, let's say, baseline constant. That'll shift it up or down. And as we'll see, that's going to be based on the average value of the function over one period. So a sub 0. And then let's start adding some periodic functions here. And so let's take a sub 1 times cosine of t. Now, why am I starting with cosine of t? And I could also add a sine of t. So plus b sub 1 plus b sub 1 of sine of t. Why am I starting with cosine of t and sine of t? Well, if our original function has a period of 2 pi, and I just set up this one so it does have a period of 2 pi, well, it would make sense that it would involve some functions that have periods of 2 pi. And these weights will tell us how much they involve it. If a1 is much larger than b1, well, it says, okay, this has a lot more of cosine of t in it than it has of sine of t in it. And that by itself isn't going to describe this function, because we know what this would look like. This would look like a very clean sinusoid, not like a square wave. And so what we're going to do is we're going to add sinusoids of frequencies that are multiples of these frequencies. So let's add a sub 2, so another weighting coefficient, times cosine of 2t. This has a frequency of 1 over 2 pi. This has twice the frequency. This has a frequency of 1 over pi. And then a sub 3 times cosine of 3t. And I'm going to keep going on and on and on forever. And I'm going to do the same thing with the sines. So plus b2 sine of 2t plus b3 sine of 3t. And you might be saying, well, okay, this seems like a fun little mathematical exercise, but why do folks even do this? Well, this was first explored, and that they're named series like this, infinite series where you represent something by essentially weighted sines and cosines. This was explored originally by Fourier, and they're called Fourier series. And they were interesting to him in the study of differential equations, because a lot of differential equations are easy to solve when you involve sines and cosines, but not as obvious to solve when you have more general functions, like maybe a square wave here. But if you could represent that square wave as sums of sines and cosines, then all of a sudden you might be able to find more general solutions to your differential equations. Another really interesting thing about this, and this is really the foundation of signal processing, it's very it's heavily used at electrical engineering, is you can view these coefficients as they're weights on these cosines and sines, but another way to think about it is they tell you how much of different frequencies that this function contains. So for example, if a1 is much bigger than a2, then that tells you that that function contains a lot more of the 1 over 2 pi hertz frequency than the 1 over pi frequency. Or maybe a2 or maybe a3 is bigger than a1 or a2. And so you can start to say, hey, this helps us think of a function not just in terms of the time domain, which f of t does, but it can start bringing us to saying, well, how much do we have of each frequency? And as we'll see with Fourier series and eventually Fourier transforms, that's going to get us into the frequency domain, where we can start doing some signal processing. So we're going to explore all of that in future videos. In order to understand how we can actually find these coefficients, we're going to review a little bit of our trigonometry, especially integrating trig functions. And then we're going to solve for these, and we're going to see how good we can approximate our function f.